Also, thanks for the invitation. And this is Hongxiang. I'm from Pacific Northwest Election Lab. And good morning, everybody. I'm going to talk about some work on the uncertainty characterization and regionalization for community net model version 5. Focus on the hydrologic prediction. So this focus on stream flow across the United States. First, I want to say this is a teamwork. This is a teamwork between Pacific Northwest Election Lab and Cornell University, and also with help from Anchor. And this project was sponsored by the DOE Office of Science, Multi-Sector Dynamics. Over here, okay. Here I'm going to review the uncertainty characterization work we have done in the previous 3 years. And this UC work has been done into 3 phases. So in here, I'm going to talk about the key finding from all the 3 phases. So phase 1 is first, we're going to have a large ensemble diagnostic evaluation of CL Model 5 hydrologic parameter over 464 basins over the CONUS. So this one gave us more insight on the model performance and what are the sensitivity parameters and how do they perform in different regions. And in phase 2, we're going to characterize the effects of the meteorologic forcing selection and hydrologic parameter uncertainty on hydrologic prediction. So you're going to understand what are the relative importance of selection of meteorologic forcing or the uncertainty compared to the hydrologic parameter uncertainty. And finally, phase 3, we're going to scale the basin scale to the whole corner scale, and we want to generate 1s degree cell by cell behavior parameters. So we can enhance the hydrologic prediction for the corners. So also I want to say that I have not done direct data simulation in this work, but I hope this UC work can help this community too. So here is our study area. So we configure CL Model 5 with both the basin scale and also the corner scale. You can see the basin scale on the left figure with carefully select 464 camel basins. That's all nature flow basins over corners to represent different hydroclimate regimes. And then we classify this basin into 7 clusters for regional access using AI/ML clustering. On the left picture, you can see different color, show different clusters. And finally, we extend the cluster into the corners at 1s degree cell. That's on the right side, also different colors show different clusters. So in the first phase for the large ensemble diagnostic, so we choose a very comprehensive list, including a total of 27 diagnostic area metrics. So the table on the left, you can see we have different temporal scale from daily to monthly, and also water annual balance, and also different hydrological regime, such as low flow, high flow, and different seasons too. So why we did this? Because different error metrics can answer different questions. So you don't calibrate based on the NSE or KGE, but depends on your sets question. Like for our multi-sector dynamics, we focus on the drought. So we really care about the low flow regime, how they perform. And if you're a reservoir operator, you care about the monthly time scale, more monthly time scale. But if you're flood management, you may care more about short-term flood peak estimations. So we're going to see the results were different to different metrics. And for the community land model, here's a table list of total 15 hydrologic parameters. This is all hydrologic parameters. We want to include as comprehensive as we can, but also consider our computation demand and computation resource. So in total, we identify 15 hydrologic parameters that including surface or surface runoff, subsurface runoff, soil moisture, snow, canopy water interception, and evaporation. And this 15 hydrologic parameters are shown in the table on the left. selected by our previous work and also some expert judgment from the community land model developer and our experience. And for each parameter set, we draw 1,500 ensembles using 19 hypercube sampling. So each ensemble have 15 parameter values. And then we develop the we call the CL modified benchmark hydrologic data set that were divided into 3 parts. The part 1 is called a default parameter simulation. So in this one, we just want to understand if we don't touch any hydrologic parameter, what are the performance according to different metrics. So we have all the data set stored in the archive in the we call it MSD multi-sector dynamics live is open public open access repository. So you can have all the data set there. We archive the time series flow, ET, also the different error metrics for the default parameter simulation. And then we have the large ensemble parameter simulation too. So also we have different faults I will show later. For different parameter set, you can also archive all the ensemble simulation there. And third, we're going to give you the sensitivity parameter and also what are the sensitivity score. And finally, we develop the behavior parameter set, which can be partitioned using the data simulation work. Okay, here's the results. The first one showing the default parameter simulation. So that's our baseline, right? So default parameter yields strong regional difference. Here I show in KGE and the flow volume bias matrix. Left picture showing the daily flow KGE, monthly flow will show different results, but similar pattern. You can see they have some scale on the west coast, some scale on the east, northeast, southeast, and some scale on the Midwest. But they have some moderate performance in the Great Plains. That's not surprising because it's really dry regions, very challenging on stream flow prediction, and also some underperformance on the Rocky Mountains on the snow dominant regions. So this on the daily flow KGE. So on the right side, I just want to point out, even for the West Coast, if you have a good KGE score, and also on the flow volume bias, that's on the water balance. So you have a annual scale, you have a really small bias, but if you focus on the low flow, so this on the summer flow in the Pacific Northwest, you care about the water temperature, like low flow volume, they have a significant underestimation. So that means if you use a different metrics, but it's different for your science question, so you may get some biased results. So the example is here, the summer flow and the low flow regime, they show really underestimation, but they show good on the annual water balance. And this picture showing the 464 basin sensitivity score to monthly root mean square error, the IMC metrics. So this focus on the high flow. And the row means different basin, and different color means different parameter, like from surface parameter to its evaporation parameter. And I also classify by the different region from northeast to the southeast. So in this picture, you can clearly show some regional patterns related to the model structure, such as surface parameter, so sensitivity to high flow metrics in most regions, such as Northeast, Pacific, Rockies, Great Plains too, but not in Great Lakes or Midwest regions. Instead, the soil porosity, they show the most sensitivity score in the Great Lakes regions. And this can be different to different metrics. And here is going to show in the at site and regional sensitivity score to other metrics. The left picture shows the sensitive score to the annual flow metrics. Now you can see the surface parameter is not that important in most regions. So if you take a look on the more red color, show more high sensitivity score. So the canopy interception parameter is more important, like in the northeast, in the southeast, where maybe have more diseased forest, and some other parameter, also the canopy parameter is more important in the Pacific Northwest. So it totally changed if your metrics change. And the picture on the right showing the sensitivity score to different metrics from number 1 to 28. So I don't read details here, but you can see the red color are shifting in different metrics. So the conclusion is you need to find out the metric for your science question and then identify what are the sensitive parameter and what are the regions and what are the behavior parameter. Then after sensitivity analysis, we developed the behavior hydrologic parameter set to different metrics. First as a basin scale, and here the red color means observation. The blue color means default simulation. This is for the regional scale. This is for the Rocky Mountain regions. You can see they have some bias here. And green color showing the prior range. So there's a large uncertainty without any constraint on the parameter set. If we take a look on the Great Lakes region, it's more clear. You have a large uncertainty in the gray shade. And then you have one constraint on the water balance, like annual volume blown by less than 10%, less than 10%. You can reduce uncertainty. And then you have two constraints with a monthly NSE like higher than 0.5. You can fit the constraint to the purple color, more close to the observation, much more close to the observations. So this is really interesting, but also show the regional difference, such as in the Pacific Northwest. We find out on the 15 hydrologic map we identify, no matter how we constrain, it can never close to the observation. That's showing something interesting thing into the model structure. Maybe the soil depth is too slow or too shallow to hold the base flow in the summer. So this can give us some insight into the model diagnosis. And also interesting in the Rockies, the peak flow are similar, not that difference, but they have a timing mismatch, and we cannot calibrate the parameter to fit the time to get the time works. So there may be some other slow process we need to take a look into this. And currently they have a really early melt, and the time is a 1 month early time, 1 month early melt. So this can give you some insight into the model structure and to the further work, how we can enhance our hydrologic prediction. And on the phase 2, not only we focus on one faucet data, then we focus on the 5 commonly used faucet data, including NLDS, Wharf dynamic driven by ERA5, Livla dataset, DayMed dataset, and Prism dataset. The 5 commonly used faucet dataset in the data simulation work or climate change impact work. And then we have 1500 hydrologic parameter set input the CM model 5. And then we want to compare what are the relative role control your hydrologic prediction. We find out really interesting work. I just highlight 2 flow regime. Low flow quantile, 0 to 10, and high flow quantile, 90 to 100%. More green color, yellow color, more faucet dominate. More blue color, more parameter dominate. So we can see on the low flow regime, you can see on the basin scale is more parameter dominate. That means calibrating on address uncertain hydrologic parameter is more important in your drought work, but it's less important if you're focused on the peak flood or monthly high flood reservoir operation on the flood management. You should care more about address uncertainty, the faucet uncertainty. And finally, we developed the cell-to-cell spatially distributed behavior hydrologic parameter set over coldness, which can be input into the CM model 5 for the large scale prediction. And on the left one, top figure, we show the default parameter on the Kama basins, and right one showing the default parameter for the coldness. Kama basin were based for the evaluation because we have observations. Very similar pattern high flow in the Pacific Northwest and Northeast. And on the bottom one, we show our developed behavior parameter. We call it hybrid method. No details here, but the behavior mean minus the default parameter set. We demonstrate user observation is really improve the performance. So we can say we address a lot of overestimation in the Pacific Northwest, the Midwest, and then we move to the grid cell level and the color scale too. Pacific Northwest and Midwest and Northeast. We show very similar pattern to show our performance on the enhanced hydrologic prediction. And this picture shows how the behavior parameter looks like service parameter and canopy parameter. They show very easily identified, but other parameters show more parameter equivalence issues. They are less easy to be identified, and this can be helpful to in the ensemble comp filter or the particle filter use dual state parameter estimation. And thank you. I stop here.
Thank you